We've all seen it in a video game, a character clipping through a wall, or a stuttering frame rate where the engine fails to keep up. We call these glitches. But some of our most rigorous physics experiments suggest these same anomalies exist in our own reality. Classically, firing solid particles through two narrow slits creates two parallel clusters, landing exactly where the laws of motion dictate. But in 1801, Thomas Young discovered light behaves differently, traveling through both slits as overlapping ripples, creating a multi-band interference pattern. In the 1920s, researchers fired individual, discrete electrons through those same slits, one at a time. Even with no other particles to crash into, the hits built up into that same wave interference pattern. A single solid particle was somehow passing through both slits simultaneously. When physicists placed detectors at the slits to see which path the particle took, the pattern vanished. The particles immediately returned to acting with solid marbles, forming two simple clusters. The act of measurement itself forced the particle to choose a single path. Reality behaves like a system that only calculates a definite state when it is prompted by an observer. The universe appears to stay in a blur of possibilities until a measurement forces the resolution. Video games optimize their performance using a technique called lazy rendering. The engine only fully computes the objects within the player's field of view. By leaving the unobserved environment as simplified data, the system saves massive amounts of processing power. This mirrors the quantum observer effect. Reality remains a probability distribution, a simplified placeholder, until an observer looks at it, forcing the universe to render the particle into a specific location. Every processing system has a maximum rate at which information can propagate. In our universe, we know this as the speed of light. Light's speed remains constant regardless of how fast the observer is moving. It is an irreducible, absolute ceiling that prevents any piece of matter from exceeding roughly 300,000 kilometers per second. An unbreakable, invariant speed limit behaves like a hardware artifact, a constraint imposed by the system's architecture, rather than a property of the objects moving within it. Zoom in far enough on any digital image, and the smooth curves break down into a grid of pixels. Physics reveals a similar resolution limit at the Planck scale. Below 10 to the negative 35 meters, space itself becomes discrete, an indivisible grid rather than a smooth continuum. This architecture includes specific preset variables. The fundamental constants governing gravity and nuclear forces are calibrated with suspicious precision. These values are fine-tuned to the exact narrow range that allows for the complexity of stars, planets, and life. Einstein famously struggled with quantum entanglement, calling it spooky action at a distance. He couldn't accept that measuring one particle could instantaneously change the state of another across the universe, seemingly faster than light. But in a computer, two variables can share the same memory pointer. No matter how far apart they are rendered on the screen, the processor sees them as the same piece of data. Entanglement reveals a reality where spatial distance is a rendered projection. Two objects that appear miles apart on the screen can remain inextricably linked together in the underlying code. Black holes provided another clue to this architecture. In the 1970s, researchers found that the information capacity of a black hole is determined by its two-dimensional surface area, not its three-dimensional volume. This discovery led to the holographic principle, the theory that our entire 3D universe is a projection of information stored on a distant 2D boundary. This redefines the double-slit experiment. The paradox of a particle being in two places at once resolves if we treat the particle as a 3D projection rather than a solid object. In a 2D substrate, a single bit of information has no 3D location. It can be projected to multiple coordinates simultaneously in the rendered output. Nick Bostrom's 2003 trilemma took these physical clues into the realm of statistics. He argued that if civilizations survive long enough to run ancestor simulations, the number of simulated minds will eventually dwarf the number of biological ones. This statistical probability has led modern thinkers like Elon Musk to conclude that there is a 1 in billions chance we are inhabiting the original base reality. We see this trajectory in our own history. We went from the 2-pixel paddles of Pong to photorealistic, persistent virtual worlds in just 40 years. If we assume any continued rate of improvement, simulations become indistinguishable from reality. Physicist John Archibald Wheeler summarized this shift in his concept, it from bit. He argued that every particle and every field of force derives its existence from the registration of information. Information forms the fundamental layer of existence. Matter is not the substrate of the universe. It is the manifestation of binary choices and data. The double-slit experiment showed us a universe that conserves its resources, only computing the physical world when a measurement forces the resolution. It reveals a reality that isn't just observed by us, but generated for us.